In this class, we'll be discussing lecture slides number 3AB, and in this lecture we are discussing um, from slide number 10, the co-channel interference in system capacity. So before starting from slide number 10, I'd like to revise what we did in the last lecture. We are discussing mainly channel assignment strategies in wireless communication and the concepts of cellular structure, neighboring cells, sectoring, and clustering. All these frequency reuse, all these concepts were discussed. Also, dynamic channel assignment and fixed channel assignment, these are the types that we discussed last time. You are also now well aware of handoff, that when a mobile station moves from one cell and the call is in progress, so how the BTS from one BTS the services are shifted to the other BTS. So, and how how those decisions are made. So we have discussed that in the last lecture. This one shows an example that if you have a total bandwidth of 33 megahertz and you have 25 kilohertz simplex channels, and for that, how you compute the capacity of the system, like when you use 4 cell reuse, 7 cell reuse, and 12 cell reuse. And in the second part, if we include control channels, so we discuss all these in the last lecture. So let's start with this slide number 10 of lecture 03AB of wireless and mobile communication, and the topic is co-channel interference and system capacity. So the first thing we call frequency reuse factor, 1 over n. Consider a cellular system which is a total of S duplex channels available for use. So in the last example, I told you that a simplex channel of 25 kilohertz is to be used. So when you multiply that by 2, you get a duplex channels of 50 kilohertz. It means that 2 subscribers, they are occupying one channel from the total bandwidth, and that total the bandwidth of that single channel is 50 kilohertz. So if you have such S number of duplex channels, if each cell is allocated a group of K channels, now in a cluster, for example, there are 7 cells, and each of the 7 cells is allocated K number of channels. Remember the variables, we have S duplex channels available for use, and in each cell there are K channels available for use. If the S channels are divided among N cells into unique and disjoint channel groups, which each have the same number of channels, the total number of available radio channels can be expressed as S is equal to Kn. So the total number of available radio channels S is equal to Kn. So if a cluster is replicated m times within the system, the total number of duplex channels C can be used as a measure of capacity and is given by for m times replicated clusters, we have the total capacity C is equal to ms. So for example, in the system we have two clusters, so your bandwidth is 2 times, you are using the bandwidth 2 times, and hence the capacity is doubled. And one total, like in this case the total 33 megahertz bandwidth was there. If you use it only once, so 33 megahertz divided by 50 kilohertz is the total number of channels in a very simple situation. But if you are including replicated clusters, so if m is 2, that 33 megahertz divided by 50 kilohertz will be doubled, and that would be then the capacity. So the capacity, which means that how many subscribers were provided services, maximum subscribers, the maximum number that the number of subscribers that can be provided services. The capacity of a cellular system is directly proportional to the number of times a cluster is replicated in a fixed service area. Very simple. Consider one sector of Islamabad, for example H11. If you divide H11 into 4 clusters, and in each cluster you are having, for example, those 33 megahertz bandwidth, so you repeatedly using that bandwidth 4 times, and you have m times s, the total capacity, so like 4 times. So in sector 1 uses, and subsector 1 and subsector 2 and subsector 3 and subsector 4 clusters, and they are repeatedly using the same bandwidth. The factor n is called the cluster size. If the cluster size n is reduced while the cell size is kept constant, more clusters are required to cover a given area, and hence more capacity. A larger value of C is achieved. So now we want the maximum value for C, a larger value of C. We want the more capacity. So for that, simple relationship between these variables, if the cluster size n is reduced, so again if you reduce the cluster size, it means that m is bigger. Larger value of m and bigger value of m will give you bigger value of C. I hope this is not difficult, but you just remember these variables: C for capacity, M for number of clusters, S, which in other words is Kn, and K is the number of channels allocated to each cell, and N is the number of cells in a cluster. So for example, I would like to do some calculation here in order to make things clear for you. If this n is 7, if n is 7, okay, so 33 megahertz is the total bandwidth. Those 33 megahertz are divided into 7, so that is the bandwidth of, sorry, the number of channels for each cell, and that is k. Each cell is given k channels, so 7 cells, so total s. S is S channels are divided among n cells, because cellular system which is a total of S duplex channels. So frequency reuse implies that in a given coverage area, which I mean like H11, the whole sector of Islamabad, there are several cells. So if you have 4 clusters, so there are now 28 cells in our assumed case that use the same set of frequency, okay, and repetition is 4 times. These cells are called channel cells, and the interference between these signals from these cells is called co-channel interference. I have previously told you the concept of co-channel interference from the diagram, but now it's very much clear that since we are doing repetition, we want to increase the capacity, we have to reduce the cell size, or we have to increase the number of clusters. The number of clusters increasing means that co-channel interference is there. Unlike thermal noise, which can be overcome by increasing the signal to noise ratio, co-channel interference cannot be combated by simply increasing the carrier power of transmitter. This is because an increase in carrier transmit power increases the interference to neighboring co-channel cells. To reduce co-channel interference, co-channel cells must be physically separated by a minimum distance to provide sufficient isolation due to propagation of the signal. So over here, I'd like just to give you, just to show you again the diagram. I think we can have it from this slide. The bigger one, this one. So what has been said? We have A, this one, and then when we move by this distance, then we have another cell. Now A is a co-channel cell with this A, which is a co-channel cell with this. So all these A cells are co-channel, which means that they are using the same frequency and providing services to the to their users. So interference and the distances between these, and obviously the size of the cell as well as the size of the cluster, that will make the you must have an optimum value for all these parameters. I repeat, since they are co-channel, A and A are co-channel cells, there must be interference between them. So in order to combat that interference, the size of the cell, the size of the cluster, the transmitting power, and the isolation between these antennas in terms of propagation is there must be an optimum value for each of them. You cannot increase the transmit power too much. If you do so, this antenna will enter into the region of that antenna, and then that's not good. That's the co-channel interference. So you must have limit this to some distance as well as limit that to some distance, and there must be some marginal distance between the two in order to combat co-channel interference. So the first option is to remember that you that the carrier transmit power cannot be increased as much as you want. That is creating problem. So when the size of each cell is approximately the same and the base station transmit the same power, the co-channel interference ratio is independent of the transmitted power and becomes a function of the radius of the cell and the distance between centers of the nearest co-channel cells. By increasing the ratio of d over r prime, the spatial separation between co-channel cells relative to the coverage distance of a cell is increased. Okay, spatial separation means that the separation in terms of xyz, in terms of space, and as I said that two co-channels must be isolated from each others in terms of some minimum distance, marginal distance between the two. So if r is the radius of the cell and d is the distance between the centers of the nearest co-channel cells. So I'll go here again. I'll use now some other a. This is r, which is the radius of this cell, and from the center to this is d. So this distance is d and r is the radius of a cell. You see, if r is the radius of the cell and this is the distance between two channels, or d is like this one. So you see, if this is d and this is r, so keeping this ratio to a certain number, which is 3 times n under the root d over r ratio, if that ratio is maintained at a certain value, then we can optimize these two parameters by you just read it. When the size of each cell is approximately the same, okay, in the cellular architecture you see each cell is of the same size and they are homogeneous, like similar in look as well as in size, in structure, and in shape. The base station transmits the same power, ideally assuming that every antenna at the center of the cell is transmitting almost the same amount of power. The co-channel interference ratio is independent of the transmitted power and becomes a function of the radius of the cell and the distance between center of the nearest co-channel cell. So if you just take this ratio d over r. So by increasing this ratio, the separation between co-channel cells relative to the coverage distance of a cell is increased. Now you can see that if you increase r, this ratio will become smaller, and if you increase d, so it will become large. So how you can do? Interference is reduced from improved isolation of HF energy from the co-channel cells. The parameter Q, which is called the co-channel reuse ratio, is related to the cluster size for hexagonal geometry by this 3n under the root. So you see here, a small value of Q provides larger capacity since the cluster size n is small. If n is small, Q is equal to what? 3 under root. 3 times n under root. So if n is small, Q is small. Okay, Q is 3 times n under root. If n is small, Q is small. Large value of Q improves the transmission quality due to smaller level of co-channel interference, and there must be an optimum value. A trade-off must be made between these two objectives in actual cellular design. So if you just use this formula, Q is equal to 3n under the root, and you will find that for different n, what's the value of Q. So if you are using I is equal to 1, j is equal to 1, so by the formula this n is equal to 3. The formula is I square plus j square plus ij, and that will gives you 1 plus 1 plus 1, 3. So for 3 times 3 under the root is 3. So for n is equal to 3, the co-channel ratio Q and n is in the cluster size, and the co-channel reuse ratio, they are the same. Otherwise, when you increase n, you have little bit increase in Q, further increasing n, more increase in Q, and larger Q means it will improve the transmission quality. So let I naught be the number of co-channel interfering cells, then the signal to interference ratio for a mobile receiver which monitors a forward channel can be expressed S to I is equal to S divided by all the channels. I naught be the number of co-channel interfering cells. Not only we are using interference, we are not using interference, we are using actually talking about co-channel interference. Okay, I have made that concept very clearly so many times, where S is the desired signal power from the desired base station, and II is the interference power caused by the ith interferer co-channel cell base station. So which of the two powers are interfering with each other, that's what is very important. So this interfere with the power of this. So here is the channel power of this cell, channel power of this cell for each cell, but we are not counting that. We are only taking a signal from here will interfere from a signal from this one, and there would be signal from these parts as well, but they are not co-channel and they are not interfering with each other. So it's very important to find to use the values from the interfering co-channel cell, ith interfering co-channel cell. And why we have used I from 1 up to some certain number? Because of the very clear concept that this guy in the middle will get interference from this one as well as this one, as well as this one, as well as this one, and this one, and this one. So if it's in the middle, its signal will be will face interference from 1 2 3 4 5 6 co-channel cells in the neighborhood. So we need to take little interference of this guy and then that guy and this everyone around it. So that's why we have to use this from I1 to 6 and the interference of each of the cell, co-channel cell. Then propagation measurements in a mobile radio channel show that the average received signal strength at any point decays is the power law of the distance of separation between a transmitter and receiver. The average received power P at a distance d from the transmitting antenna is approximated by received power is P naught d over d naught raised to the power minus n. Here minus n is very important path loss exponent, very important number. It is called the path loss exponent. N is path loss exponent. Now P naught is the power received at the close-in interference point in the far field region of the antenna at a small distance d naught from the transmitting antenna, and n is the path loss exponent. So this exponent, just considering all the propagation measurements, all the propagation mechanism we have studied in the last in the previous course. So over here we are just taking a fixed number. Obviously it's a very approximated number, but that approximated number is giving you is including every propagation phenomena: the effect of refraction, the effect of vegetation, the effect of scattering, the effect of reflection, all of those inside one value, and that value is minus n, or you can say n, and that n is called path loss exponent. So then this simplified link equation is just relating d and d naught and p naught and pr. Like you can write them in this format, that this is in dBm, received power is whatever you have transmitted, and you take away from it this, which is got propagation effect and distance effect. And since we are taking d over d naught, the ratio, so you see what is d and what is d naught. D naught at a small distance d naught from the transmitting antenna. So this is distance. Okay, let me see if there is any diagram. No. Okay, I will draw it myself. D over d naught, keep it in mind. Okay, for example, the user of this is here. So from the center to this, that distance is d naught, and obviously d is from the interference from the other to this. So that's why we are taking the ratio of d over d naught. I'll clear it in another diagram next time. At the moment, sorry, we are on this. Let me finish this and we will discuss later on. FDI is the distance of the ith interferer. The received power is proportional to di exponent minus n. So you see we have all these quantities now. When the transmit power of each base station is equal and the path loss component is the same throughout the coverage area, signal to interference for a mobile can be approximated as. So we know now this signal to interference ratio, and this tells us, this number tells us that how much interference, which part is strong, the signal is stronger or the interference signal is strong. So transmitted signal compared to the interference signal, just like SNR. SIR is very important parameter, and this is given by this equation, d over r divided by I naught and n. So you know all these four parameters are, if you just not considering d and r, you can use n, which is again will simplify. But from here, you know d, the distance between the two co-channels, the center of the co-channels, you know r is the radius of the transmitting cell, n is the path loss exponent, and I naught is the part that is interfering with the from the co-channels of the or in the co-channel um, of the transmitting cell. So you see, from 1 to I naught di, all the di, all the 6. I will draw another. You see here, I repeat, from this point, from A, capital D is the distance from here till here. And what is the interference? I naught. I naught is the sum of all the interfering signal from this station, this cell, this cell, this base station, this base station, this one, and this one. And all the 6 are added up because all of them are interfering over here. So that's why, and they are fighting, or they are like competing with the signal strength of this. So the user is here, and the user is interrupted by 6 signal and 6 interfering signal, and the user is getting one strong transmitting genuine signal from its transmitter. So the same story is for everyone, but obviously this one will have its own neighborhood like this, and on its neighborhood it will have some 6 I interferences. So I hope you will have understand this. So this is it for today. See you later. Thank you.